Episode 11. Title of the course is Advanced Materials Science, Unit 3. In this episode 11, we will discuss different types of dielectric materials. Based on the application, we have two types of dielectric material. One is active dielectric, that means ferroelectric, piezoelectric and pyroelectric materials. Another one is passive dielectrics, that means electrical insulating material. Active dielectrics are ferroelectric materials. Active dielectrics are the materials which can be adapted to generate, amplify, modulate and convert electrical signal. This can store electrical energy. Next one is passive dielectric or insulating material. The function of insulating material is to the flow of electric current. Classification of insulating material. Insulating material are classified into three categories. One is solid insulating material. Example: mica, rubber, PVC, polythene, glass, cotton, silk, wood, ceramics, etc. Second one is liquid insulating material. Example for is varnish, transformer oil, cable oil, silicon fluids and fluoroorganic fluids. Third one is gaseous insulating materials. Example: air, hydrogen, nitrogen, halogen and sulfur hexafluoride. Let us see first the important solid insulating materials. Ceramic insulating materials. Ceramics are also be called potter's earth or clay. It is the product which is produced by the action of fire on the earthly material. Structurally, ceramics are crystals bonded together. These are generally inorganic, non-metallic, ionic or covalent compounds. Ceramics can be produced by mixing finely grounded clay and metal oxide with water just sufficient to make a paste which is shaped according to the requirements. This mold is finally dried and fired at temperature range between 1200 degrees Celsius and 1700 degrees Celsius. Ceramics are hard, strong and dense. They are completely stable at high temperatures. They are not affected by moisture and by chemical action except with strong acids and alkalis. Ceramic materials can be classified as clay products, refractories and glasses. Porcelain is the important clay product. It is used in line insulator, transformer, bushing pins, switches, plugs, fuse holders and sockets. It is also used to make discs for electrical stove, kettles, etc. Beads to insulate heating conductors and conductor connecting heating elements. Materials subjected to high temperature which do not disintegrate are commonly known as refractory materials. Alumina is an important refractory material. It is primarily made of aluminum oxide. Its manufacturing is difficult to extremely high firing temperature, which is of the order of 1750 degrees Celsius. It has high compressive strength, absorbs less moisture and is excellent in heat conduction. It is used in high temperature appliances like furnaces. Silica gas, Pyrex and fiberglass are the important glass insulating material. Glass is an inorganic material made by the fusion of different oxides like silicon oxide, zinc oxide and magnesium oxide. Glass is brittle and hard. It has low dielectric loss and has good mechanical strength. It is highly chemical resistant to most corrosive agents and is good insulator with good appearance. It is insoluble in water. Glass is used as dielectric in capacitors. It is used as insulator in radio and television tubes, electrical lamps, laminated boards. Glass is employed for insulation in extra high voltage lines having voltages above 100 kV. Mica is a material compound of silicate of aluminum with silicates of soda, potash and magnesia. It has high dielectric strength and low power loss. It is not affected by moisture. It is rigid, touch and strong. Mica sheet are used as insulating between commutator segments. Thick mica tapes is used for tapping the coils of high voltage alternators. It is also used in electrical irons, hot plates and insulating purposes. Mica flakes are used in motor, slot linking and transformers as insulation. Mica paper is used as insulation for field coils of rotating machines. Next one is PVC material. When acetylene and hydrogen chloride are combined in presence of catalyst at temperature of about 50 degrees Celsius, polyvinyl chloride, that means PVC resin, is produced. Due to having good mechanical and electrical property, it is widely used in insulator of wires and cables. PVC films, tapes and sheets commonly used for insulation in dry batteries, conductors and cables. Next one is rubber. Rubber is used to insulation of thick wires carrying high current. Further increased sulfur content and extended vulcanization treatment on natural rubber give a hard rubber product. It possesses good dielectric property and high tensile strength. It is used in the construction of storage batteries, housings and panel boards. Next one is asbestos, is naturally occurring mineral material of fibrous structure. It has high dielectric loss and low dielectric strength. Asbestos find extensive use in electrical machines because of its ability to withstand very high temperature, about 400 degrees Celsius. Further, it is also used for making of cloth tapes and paper boards for insulation purpose. It is used for covering on wire for electrical heating device, ovens, electrical irons, etc. It is used as arching barrier in switches and circuit breakers, etc. Liquid insulating materials can be divided into three groups. First one is mineral insulating oils, that is transformer oil, cable oil, capacitor oil, etc. Second one is synthetic insulating oils, SAWL, etc. Miscellaneous insulating oils is vegetable oil, Vaseline and silicone liquid, etc. Generally, liquid dielectric material have moderate dielectric strengths, but insulating liquid improve the insulating property of the other solid material by eliminating the other gases. They offer good heat dissipation media and facilitate cooling of the windings which emit heat due to losses in the winding. They are sometimes required for extinguishing arcs in certain applications like circuit breakers. Next one is mineral insulating oils. These oils are obtained from crude petroleum by distillation and have high oxidation resistance and good thermal stability. These are used in transformers and capacitors. Transformer oil is important mineral insulating oil with high dielectric strength, viscosity and cooling property. This oil is used for insulating and cooling of transformer. It transfers heat by convection from the winding and goes to the cooling surface. It maintains the insulation of windows. Nowadays, synthetic oil is used as insulator in transformers in place of transformer oil, that means mineral oil, because synthetic oils are very much resistant to oxidation and to fire hazards. Instead of pure mineral insulating oil, a mixture of mineral insulating oil and synthetic insulating oil is commonly used to get high oxidation resistance as well as reduce the cost of the oil. Next one is synthetic insulating oils. When we compare this with mineral insulating oil, the properties are, but these oil are very cheap and non-inflammable. Due to longer life and safer in operating conditions, synthetic oil is used as coolant and insulant in HV transformers. Particularly, SRUTHIs have thermal stability up to 110 degrees Celsius and are manufactured from chlorinated hydrocarbons. Next one is miscellaneous insulating oils. Silicon liquids have stability up to 200 degrees Celsius and are costly. The dielectric strength of this liquid is same as that of mineral oils and power factors is very low. They are used in HV transformers. Further, these are used to increase the surface resistivity of ceramic insulator. Vaseline has high viscosity and high dielectric constant. It is used for impregnation of papers used in capacitors. Next one is gaseous insulating material. Air is the most important material available in nature and is used for insulation between the two conductors of high voltage transmission lines. It is also used in air capacitors. The power loss is practically zero. The dielectric constant of air is increased linearly with the increase of pressure. Air can be used as insulation only in the low voltage application. Nitrogen is chemical inert. It prevents oxidation and reduces the rate of loss. For example, in oil-filled transformers, the nitrogen is used to replace oxidizing atmosphere. This is also used in capacitors and in cables under pressure. Inert gas are used in electronic tubes and discharge tubes as insulators. Sulfur hexafluoride is formed by burning of sulfur in fluorine atmosphere. It has high dielectric strength and non-inflammable. It has superior cooling property those of air and nitrogen. It has highly chemical stability up to 100 degrees Celsius and is used in transformers and electric switches. Further, it is also used in voltage stabilizer and X-ray apparatus for insulation purpose. Next, we will discuss about ferroelectric materials. Materials which exhibits electrical polarization even the absence of applied electric field are known as ferroelectric materials. These have permanent dipole moment in each atom or molecule. The dielectric constant of these materials are some 3 order of magnitude larger than ordinary dielectrics. Ferroelectricity refers to creation of enormous values of induced dipole moment in a weak electric field, as well as existence of electric polarization even in the absence of applied electric field. Ferroelectricity is a result of dielectric hysteresis. Since these materials exhibit hysteresis effects similar to those observed in ferromagnetic material, they are called ferroelectric material. Barium titanate BaTiO3, potassium dihydrogen phosphate KH2PO4, ammonium dihydrogen phosphate NH4H2PO4, lithium niobate LiNBO3, and salt NaKC4H4O6.4H2O are the typical example of ferroelectric material. Properties of ferroelectric material. First one is ferroelectric materials can be easily polarized even by very weak electric field. They exhibit electric hysteresis. Lagging of polarization behind the applied electric field is called dielectric hysteresis. Ferroelectricity is a result of dielectric hysteresis. Ferroelectric materials possess spontaneous polarization, which is polarization that when the applied field is zero. The possesses permanent electric dipoles and internal electric field which develop spontaneous polarization at ferroelectric Curie temperature. Ferroelectric material exhibit ferroelectricity when the temperature capital T less than or equal to capital C, where capital TC is ferroelectric Curie temperature. When T is greater than T base C, they are converted into paraelectric material. They exhibit domain structure as in the case of ferromagnetic materials. Ferroelectric material exhibit piezoelectricity. Piezoelectricity means the creation of electric polarization by mechanical stress. Pyroelectricity means the creation of electric polarization by thermal stress. Piezoelectric material are used to make pressure transducer, ultrasonic transducer, and microphones. Example: quartz, lithium niobate, barium titanate among the crystalline material, lead zirconium titanate, calcium barium titanate, and lead barium niobate among the ceramic material. Pyroelectric material are used to make high sensitive infrared detectors. Example: barium titanate, triglycine sulfate, lithium niobate, lithium titanate, and polyvinyl fluoride. Some ferroelectric semiconductors like BaTiO3, SRTiO3, BaTiO3, PbTiO3, and SRTiO3, PbTiO3 are used to make compositors, which are used to measure and control temperature like thermistors. They have positively temperature coefficient of resistance. Electrodes are ferroelectric material and electrostatic analog of permanent magnets. Electrodes possess a gross permanent electric dipole. They are manufactured from certain types of waxes, plastics, and ceramics. When these waxes are subjected to high electric field, that means 10 to the power 6 capital V by M, they are polarized in their molten state and retain a permanent polarization after solidification, even though the external polarization field is removed. Electrodes are used in capacitors, microphones, and gas filters to capture submicron particles by electrostatic attraction. Further, the electrode bondages are used over the fractured bones to speed up the healing process. Condition for the spontaneous polarization. Consider the equation capital P equal to n alpha base small e into capital E divided by 1 minus n alpha E divided by 3 epsilon naught. If the denominator becomes 0, we get polarization. This can be interpreted as that there is polarization even when there is no external field, or in other words, there is spontaneous polarization just as there is spontaneous magnetization in ferromagnetics. The condition for spontaneous polarization is given by capital N alpha E divided by 3 epsilon naught equal to 1. We may not conclude that with capital N alpha E divided by 3 epsilon naught equal to 1, the dielectric constant will become infinite, but we may conclude that the substance will become spontaneously polarized. Dipole theory of ferroelectricity vs. field theory. The atoms or molecules of ferroelectric material are considered to be made up of permanent dipoles in which the mutual interaction is large, which stands to align their moments. In the same way, ferromagnetic atoms, on the basis of ferromagnetic analogy, we can write capital P equal to capital N mu square capital E base I divided by 3 kT, where capital E base I is equal to local field of the material and small k is equal to Boltzmann constant. The reason for spontaneous polarization is that the field which each dipole sees is greater than the applied field. We know that capital E base I equal to capital E plus gamma into capital P by epsilon naught, where gamma is called internal field coefficient, which depends on the structure of the material, and calculations show that gamma is not a constant but depends on the dielectric constant in such a manner that gamma decreases with increasing dielectric constant. Capital P equal to capital N mu square by 3 kT into capital E plus gamma capital P divided by epsilon naught. Rearranging the terms, we get capital P equal to capital N mu square capital E divided by 3 kT into 1 minus capital N mu square gamma divided by 3 k capital T epsilon naught. Using this equation, the electric susceptibility can be written as chi base E equal to capital P divided by epsilon naught into capital E is also equal to capital N mu square divided by 3 k epsilon naught into capital T minus capital N mu square R divided by 3 k epsilon naught. It is also equal to capital C divided by capital T minus theta. Capital C is equal to capital N mu square divided by 3 k epsilon naught, and theta is equal to capital C gamma. Here capital C and theta are called Curie constant and Curie temperature respectively. Since capital P divided by capital E equal to epsilon naught into epsilon r minus 1. Epsilon r minus 1 is equal to chi base E is also equal to capital C divided by capital T minus theta. This is known as Curie-Weiss law. The ferroelectric properties disappear above the ferroelectric Curie temperature, and then the material is said to be in paraelectric state in analogy with paramagnetism. Therefore, ferroelectric property will exist only when capital T is less than theta. This condition can be verified by the following way. Applying the Langevin expression for the paramagnetic gas, that means refer Langevin theory of paramagnetism, we can write for the electrical case capital P is equal to capital N mu capital L of alpha, where L of alpha is Langevin function and alpha is equal to mu capital I divided by small k capital T. For large value of alpha, the Langevin function turns to unity and polarization reaches saturation value, and so P sat equal to capital N mu. Capital P by P sat is equal to capital L of alpha is also equal to L into mu capital E base I divided by K T is also equal to L into mu divided by KT into capital E plus gamma capital P divided by epsilon naught. Spontaneous polarization exists if there is a non-vanishing solution for capital P when capital E is equal to 0. Therefore, spontaneous polarization is expressed as capital P divided by capital P sat equal to capital L into mu gamma capital P divided by K capital T epsilon naught is equal to capital L of x. Small x is equal to mu capital P gamma divided by small k into capital T epsilon naught. Here capital P is equal to k capital T epsilon naught small x divided by mu gamma. Therefore, P divided by P sat is equal to small k capital T epsilon naught divided by n mu square gamma into small x. We know that theta is equal to capital N mu square gamma divided by 3k epsilon naught. Therefore, P divided by P sat is equal to capital T small x divided by 3 theta. These equations are plotted in the same graph, and this equation represents a set of straight line which passes through origin. Therefore, 3 straight lines are drawn for capital T is less than theta, capital T equal to theta, and capital T greater than theta. Since equations are the same, a common solution for finite value would exist if there is an intersection of the straight line with capital L of x curve. Only the straight line drawn for temperature capital T less than theta intersects with capital L of x curve, and hence there is spontaneous polarization at very high temperature. That means T is greater than theta. The straight line does not intersect with capital L of x curve, but when T is equal to theta, the intersection of the straight line with capital L of x curve starts. Therefore, when capital T less than or equal to, there is existence of spontaneous polarization, where E base I is equal to local field of the material and K is the Boltzmann constant. The reason for spontaneous polarization is that the field which each dipole sees is greater than the applied field, and also here capital C and theta are called Curie constant and Curie temperature respectively. We know that theta is equal to capital N mu square gamma divided by 3 small k epsilon naught. Then finally we get the product P divided by P sat is equal to capital T small x divided by 3 theta. Graph should be drawn between small x versus P divided by P sat. When small x increases, then P divided by P sat also increases, then saturate in time of capital L of x. Dear student, thank you. We will discuss another topic in the next episode.